So during this session, we would like to discuss related to design for reliability, the reliability of systems. Now, though we talk about reliability of the products, but many a time you deal with the systems, and there could be different types of systems with different configurations, and so you need to look into reliability modeling of all these kinds of systems. Now, in today's the lecture session, I will be referring to series of chain structure and the parallel structure. So these are the two important the systems we come across in manufacturing and other systems, and we'll be just referring to the reliability modeling of such systems. Prior to discussing these two aspects, let me refer to an example. And in the previous lecture session, if you remember, we discussed at length the probability distributions for reliability modeling. There are different kinds of the probability distributions you may assume, and so we have discussed those the typical distributions normally you come across in reliability modeling. Now, we'll just cite one example, and then we'll be discussing the reliability of the systems. Now, this example is a typical example, so let me just go through this particular example. A mechanical system has demonstrated a Weibull failure pattern. That means time to failure distribution is assumed to be Weibull, and already we have discussed the Weibull distribution with a shape parameter of 1.4. That means the value of beta is 1.4 and the scale parameter of 500 days. So what is the scale parameter? Scale parameter is essentially is referred to as alpha. Determine the following, that means reliability, that the system will last for 150 days. That's the sort of notation we use. The B1 life, MTTF, mean time to failure, the standard deviation of the time to failure, the median time as well as the mode time, okay, time to failure, and the design life for a reliability of 0.95. So these are the the aspects to be looked into. So referring to the first the question, we determine the reliability with 150 days survival of the system. So we use this particular formula, that means RT equals to e to the power minus T by theta to the power beta. We have already derived this expression, so you refer to this particular expression and you just apply this formula. So if you apply this formula, you get a value of 0.8308. That means its reliability that the system will run for 150 days, that is 0.8308. The next part is the B1 life. We have already derived the expression for, we have already explained, we have defined what is this B1 life. So directly you apply this formula and you get a value of 0.99. Is it okay? So and then you say that T 0.99, that is another expressions we have already derived. Please refer to all these derivations, and then when you apply this formula you get this value, that means 18.705 days. Okay. We calculate MTTF, mean time to failure. This is theta gamma function 1 plus 1 upon beta. We have already derived these functions, okay, gamma functions, and so this is alpha. So this is essentially 500. So 500 gamma function 1 plus 1 upon beta. So what is the value of beta? that is the shape parameter 1.4, and you get a value of 455.286 days. Is it okay? So that is the MTTF. Similarly, we calculate the variance. We use this formula, and we get a value of 109,472.66. Is it okay? And so that is sigma square. So the square root, that means the positive square root of the variance, that is the standard deviation, that is 330.866 days. Is it okay? So you know the formulations. So in these examples, what we are trying to do, that means you have the corresponding data and you are trying to determine all those the parameters. Okay, so this is the t point at 0.5, that is the t median. So again we apply this formula, and the t median is 384.836 days. And similarly, the t mode, again we have derived this formula, and when we have all these values, then you get the value of t mode as 204.336 days. And the TD, similarly, you have these expressions for TD, and you get a value of 59.92. So this is a typical example. There could be many other such examples. Numerical problems, will be dealing with those numerical problems in subsequent sessions. Okay, so this is just one application. So you have been using, or you have been deriving many kinds of mathematical expressions while you go for reliability modeling of a system. So this is just a numerical problem related to some of these the formulations. Now let us let us discuss the reliability of systems. Okay, so this is the part 1, and again in subsequent lecture sessions I will be referring to say the part 2 of reliability of the systems, because you come across various kinds of systems, the varieties of systems, varieties of configurations, and it is your attempt to go for reliability modeling for all such systems. Now, what we have mentioned over here, that the components, units or subsystems within a complex system can be related to one another in series, parallel. Series parallel, that means it's a combination, that configuration you may have, or a meshed structures. Okay, so we may come across several such the structures while you try to configure your system, or in any combination of all these. Is it okay? So this is your the idea about the system structure, or the system's configuration. Now, probability concepts are applied to compute the reliability, but essentially, whenever you try to have a numerical value of reliability of a systems or a part or a component, we refer to the probability. Essentially, it's probability. While we define reliability, we have mentioned that this is nothing but the probability. Is it okay? So the probability concepts are applied, it is obvious, to compute the reliability of the system in terms of the reliability of its subunits. That means a system may consist of several one or more of the subsystems, and each subsystems may have different subsystems. Okay, and at a particular level, maybe a particular subsystems or the subsystems may have several components or the parts. Okay, so as per the bill of material, as per the product structure code, so you have to assemble those components, you have to assemble those sub-assembly to get the final assembly. Is it okay? So we have already referred to a particular term called product structure code, and prior to product structure code for the given system, you must know what is the bill of material. And the bill of material, actually this document you get from the design department. Is it okay? So now the first the type of systems you come across, that is referred to as the series systems, or the chain structure. Is it okay? Now the question is that how to measure reliability of a series systems or the so-called chain structure. In series or chain structure is the type of system, all components must function for the system to function. Okay, that means systems must run. Under what condition it runs? Because it consists of several the components, and all the components must run simultaneously, then only the system will be running. Like many missile system, okay, it may consist of some around say 4,000 components, 3,000 components. It's a very complex design, and essentially they say that this is a series structure. That means you can well imagine that to get the function from a missile, what you need to do, you need to assure that all the components, and these components in thousand numbers, so you will find that all the components must be so reliable that it must not fail at a particular point in time. If just one component fails, entire system breaks down. Is it okay? So that sort of the event must be avoided. So this is the condition. Is it clear? If the series system component failures are statistically independent, is it okay? That means what you have, that means for each of these components, it has its own time to failure are the distributions, or related to time to failure, it has its own parameter values like the different the mean value and the different standard deviation values. Okay, so and we say that the function of one component no way is affected by the function of the other components. Okay, so we may assume that they are all statistically independent. Then the reliability of the system, the notation is RS of a series systems R subscript S with non-identical components is given by RS product Ri. Is it okay? That means it is product terms Ri, I equals to 1 to n. Is it okay? Where n is the number of components or the subsystems. Is it okay? And Ri is the reliability to the ith component or the subsystems. Is it okay? So what we assume that this system consists of a number of components or a number of subsystems or both. Is it okay? So so you must know the individual component reliability or individual subsystems reliability. So this is the expressions. Is it okay? So it has to be a product term. So this is the reliability of a system. So this is a typical what you can say the figure related to the series of chain structures. So you have say 4 components over here. They are they are in series, and this is you have this one, like all are interrelated, and you get the effect, and there could be several causes, there could be several types of effects, so that you must be able to monitor. Is it okay? So that means the causes of running this system, what could be the effect of running these series systems, you should be aware of. Is it all right? There could be many problems, and you need to identify the sources of these problems. So what you can do, that means for such a system, if you face a lot of problems, okay, it's like say problem related to failure. Okay, so what you need to do, you can identify the sources of the problem as well as the types of the causes. So you may use several kinds of the tools or the techniques for identifying such causes. Okay, so if the failure times of the components are exponentially distributed, then what does it mean? That means you have created the system, you have you have included all such subsystems or components. Now all these components they're in basically useful life phase. Is it okay? And if these components, that means it has all these components, they are not in the burn-in phase or in the wear-out phase. They are in the the useful life phase. So if all these components are in useful life phase, obviously you may assume that the failure rate, okay, is constant, and if the failure rate is assumed to be constant, you may assume that the time to failure distribution is exponential. So this point already we have elaborated. That means if the components have constant failure rates, this point I have already mentioned. The ith component reliability is obviously, for the ith component reliability is e to the power minus lambda it. So what is lambda I? That is basically the failure rate for the ith component. And obviously you are trying to compute the reliability for the t time period. That means whenever you say that I compute reliability for the t time period, that means I am assuring that the component will be surviving for the t time period. So what you have basically now, the system's reliability is essentially all these for the ith items. How many items you have? Obviously there are n number of items. So the system's reliability is obviously e to the power sigma I equals to 1 to n number of components in series for the systems lambda it, and e to the power minus, obviously. Is it all right? So you add all these the terms, right? So sigma lambda I into t. Is it all right? So it is sigma lambda I into t. MTTF is given by, again, 0 to infinity e to the power lambda t sigma lambda t dt. So 1 upon sigma I equals to 1 to n lambda I. Is it okay? So these simple calculations you have, and you can calculate the system's reliability as well as the mean time to failure. Hence the mean time to failure of a series systems is the reciprocal. This is the reciprocal of the sum of the series network component failure rate. So this is the sum of the failure rates. Is it okay? So how many failure rates you have? N number of failure rates. So you add them and then you take it reciprocal. So that becomes basically the mean time to failure, or MTTF. Okay. Now here is an example. So let me discuss this example. This is a typical numerical problem. Determine the minimum allowable component reliability to attain a system's reliability of 0.95. That means the system's reliability is pre-specified for a series systems. So the kind of systems that is also mentioned, consisting of 2, 3, 4, 5, 6, 7, 8, 9 and 10 identical components. Is it clear? That means a series systems may have two. So if you have just two components, two identical components, how do you define the identical component? Because with respect to the failure rate, or the first thing is identical in the sense that suppose you say that one item is identical to the next item. That means for both the items the time to failure distribution must be same, and similarly the parameter value of the distribution that you assume must also be the same. In other words, in this particular case the failure rate is also same. That's why they are referred to as that the identical. Is it okay? So for n identical components in series to attain a system's reliability of 0.95. Okay. So in general each component must have a reliability of this one, 0.95 to the power 1 upon n. Okay. So that is directly you apply the formula. Is it okay? The formula linking the the system's reliability with individual component reliability in a series systems. So you have these expressions. Now what you do? If n is 2, what will be the value of the the component reliability? Is it okay? If n is 3, that means all three components are assumed to be identical, okay, in respect of their the failure rate. So the value is 0.9831, and similarly for all other the numbers of components you consider. That means 4, 5 up to 10. So if you have 10 components in series, that what you must ensure, that means for each component, is it okay, must have a reliability of 0.9949. So it's very, very high, almost tending to 1. Is it okay? So as you might have noticed, as the number of the components in the series increases, what you need to do, that means individual component reliability value must also increase. Is it okay? So in this case, the minimum value with 2 components in series, each component must have a reliability of 0.9747. But when you deal with in the system 10 identical components in series, obviously the individual component reliability increases to 0.9949. So the difference between 0.9747 and 0.9947, you can prove that the difference is significantly different. Okay, so this is a typical example. Now the next example, let me take up the next example. A complex system has 600 components in series. I am telling you, you will come across the several sorts of complex systems, and the complexity of a systems can be defined from several perspectives. One perspective is the number of components. Is it okay? So here we are just considering the number of components indicative of the complexity of the system. So here is a system, the 600 components in series. So you can well imagine that how while you select all these components, make sure that all these components must have a very high value of reliability, that is to be ensured. Is it okay? Now obviously you must know that before you use a particular component in a system, okay, while you manufacture the system, you also must have a prior idea, okay, that what could be its possible reliability. That means you must be able to estimate it. So how do you estimate the reliability of a component? There are procedures. In subsequent lecture sessions on reliability, we'll be discussing those aspects. Okay, so for the time being, we assume that the reliability estimation procedure is known, and the value of the reliability of a given component is also known. Okay, the reliability of each individual component is 0.998. It's very, very high. Determine the reliability of the system. Is it okay? If the number of components in series is reduced to 500, normally, when you try to go for say design improvement, okay, in many ways you can go for improving the design of a system. The first, the approach should be to what extent you can reduce the components, reduce the number of components. Okay, so as you try to simplify the design, so the first thing you try to do, you try to reduce the number of components. Is it okay? So here is a case, initially you start with a design with 600 components. Now you go for improving the design, and then with an effort, what you can do, 600 has now become 500. That means 100 components are reduced. So find the reliability of the resulting system. So it's very easy. That means the system's reliability is 0.998 to the power n. So what is the value of n? N is 600 in the original system. So it has come down to just 0.3008. That means in series systems, if you increase the number of components in series, obviously the system's reliability will be significantly less. Is it okay? The system reliability is only 30.08%. If the number of components in the series system is reduced to 500, you can expect that the value of reliability will increase. And so what is that increment? Increment is just 6.75% almost. Is it okay? Around 6.6%, 7%. That means it was 30.08. Now it has become 36.75. That means almost more than 6% improvement in reliability is possible by reducing the number of components from 600 to 500. Okay. Now, what is the parallel structure? So, alternative to series structures, you have again a pure structure called parallel structure. These systems will fail if and only if all the units in the systems fail. The assumption is that not all system units are active and load sharing. Is it okay? So, that is the basic assumption. That means to run the systems, at least one subsystems or one component must run. It is assumed that the component failures are statistically independent, like in the previous case. A parallel structure reliability, okay, that means the notation is RP with non-identical units, like in the previous cases, or the component reliability is given by RP is equals to 1 minus Ri. So, is it okay? That means first you check that if all the components fail, so the system will fail. Is it okay? So, what is this reliability? Obviously, it will be RS, the system's failure reliability. Okay. So, then 1 minus Ri is essentially that it will fail. Is it okay? So, all the components will fail with individual component say probability is 1 minus Ri. Is it okay? So, I equals to 1 to n. So, this is the product term, and when you subtract this product term from 1, you get the parallel system's reliability. Is it clear? So, where n is the number of units, Ri is the reliability of the ith component or the system. So, 1 minus Ri is basically the non-reliability, or say it is a failure. Is it okay? In a period of time. Okay. So, now here one basic assumptions we are making, that is the reliability, the value, they remain same over time. Usually it is not so. That means the reliability actually becomes a function of time, reliability of a component. Here we are assuming that the value of reliability at a particular point in time remains same for all the time period. Is it okay? So, we will realize these assumptions later on. So, this is a typical the structure, that is cause and effect. So, this is these are the components you have. How many components you have? N number of components. So, this is basically the configuration. This way you replace the configuration. That means the systems will run only when any one of these components runs. Is it okay? That is the basic condition to be ensured. So, if the component failure rates are constant, then this is the equation, or this is the expressions for the reliability, reliability for the t time period. So, obviously, the failure rates are constants, that means lambda I. That means for the ith component, you have the failure rate as lambda I. Okay. Useful life phase, okay, all the components are in. So, this is the expressions, okay, because for individual reliability expression is e to the power minus lambda I t. Is it okay? Exponential time to failure distribution. And similarly, we compute MTTF. Is it okay? So, MTTF is these expressions. That means integration 0 to infinity RPT dt. Is it okay? So, this is the expressions. That means essentially you calculate the mean value. Is it okay? Starting from the fundamentals. So, these expressions you can use. So, RP expressions is already there. So, it is replaced with this one, and then you get this the value. Okay. So, MTTF further you can manipulate, you simplify these expressions, and ultimately you get these expressions. Is it all right? For identical components, the above equation reduces to this one, MTTF is equals to, that means this is a particular case, this is the generalization. So, you just note it down, this is the general expression, and a particular case is this when you deal with the identical components. That means all these components are having the same failure rate. Is it okay? So, MTTF expression is reduced to these expressions 1 upon lambda sigma I equals to 1 to n 1 upon I. In general, parallel structure improves systems reliability. That means obviously if you ask for the design improvement, you go for the parallel structure from the series if it is feasible. Okay. So, here is an example. Determine the number of identical components required in parallel structure in order to achieve a system's reliability of 0.97. The individual component reliability is given as 0.85. Determine if the desired level of system's reliability is achieved if the same components are arranged as series structures. That means a comparison with the series structures we do. So here we have this value, that means 0.99. So ultimately what you find that with 0.97, so you get a value of say of n equals to 4. Is it okay? So this is the expression, and for the series structure the system's reliability, that is r to the power n, 0.68 to the power n, that is 0.2138. So it's very less. Hence the system's reliability is not achieved with the series structure. So this is one example. So I conclude this, and just we have referred to the two kinds of systems, the series systems and the parallel systems. And in the subsequent lecture sessions we will be taking up several examples, and one particular the systems we always we refer to, and we come across such systems, that is the systems with the standby, okay, the standby components. So that part also we will discuss in the subsequent lecture sessions.